depth dilemma. Beyond the geological instability lies another engineering nightmare that compounds every calculation. As our submersible's lights fade into the crushing darkness 900 meters below, we confront a simple yet devastating reality. Water pressure at these depths increases exponentially, creating forces that no existing infrastructure technology was designed to withstand. The oppressive blackness surrounds us like a silent, leviathan force, squeezing the submersible from all sides with invisible but relentless power. What you're seeing now is the central challenge of the Gibraltar Strait, explains Dr. James Chen, marine structural engineer, as he traces his finger along a detailed bathymetric map spread across his desk. While most people focus on the narrow 14-kilometer distance between continents, they miss the crucial third dimension. The color-coded depth chart reveals a startling profile, a submarine valley that plunges dramatically from the relatively shallow continental shelves on either side. Dr. Chen points to the deepest section, marked in dark blue. The Gibraltar Strait reaches depths between 300 to 900 meters. To put that in perspective, the English Channel, where we successfully built the Channel Tunnel, has a maximum depth of just 180 meters. We're talking about a crossing that's 5 times deeper at its lowest points. On screen, we see a striking comparison. The Øresund Bridge between Denmark and Sweden crosses waters just 35 meters deep. Japan's Seikan Tunnel, currently the world's deepest undersea tunnel, reaches a maximum depth of 240 meters. Even Norway's Rogfast Tunnel, under construction and set to become the world's deepest road tunnel, will reach just 392 meters below sea level. The problem is the extreme depth, continues Dr. Chen. Water pressure increases by approximately 1 atmosphere for every 10 meters of depth. At 900 meters, we're talking about pressure exceeding 90 atmospheres, equivalent to having 90 kilograms of force applied to every square centimeter of your structure. The animation demonstrates how pressure compounds. Imagine the weight of a car pressing down on every handprint-sized area of your body, then multiply it tenfold. At 100 meters, the force is manageable. At 300 meters, it begins to exceed most conventional design parameters. At 900 meters, the pressure becomes almost unimaginable, over 1,300 pounds per square inch. The engineering implications are profound, Dr. Chen says, pulling up computer models on his monitor. Conventional tunnel boring machines are designed to operate at much shallower depths. At these pressures, we encounter problems with everything from material integrity to worker safety. The simulations show how different tunnel designs would respond to these extreme pressures. Traditional circular concrete tunnels begin to show failure points. Steel reinforcements bend. Even advanced composite materials display strain beyond acceptable safety margins. For a bridge, the challenge is equally daunting, explains Dr. Chen. The world's tallest bridge piers currently reach about 340 meters at the Millau Viaduct in France, but those are exposed to air. Underwater bridge supports create an entirely different engineering problem. The diagram illustrates how underwater bridge supports would need to contend with not just vertical loads from the bridge itself, but enormous lateral forces from water pressure, currents, and potential seismic activity. At these depths, conventional bridge support technologies simply become impractical, Dr. Chen notes. The materials, construction methods, and designs that work for shallower crossings cannot simply be scaled up. We would need fundamentally new approaches. These engineering challenges are further complicated by the seabed composition. Dr. Chen turns to a geological cross-section of the strait floor. The composition of the seabed presents its own set of challenges. Unlike the relatively soft clay that facilitated tunneling under the English Channel, large sections of the Gibraltar seabed consist of extremely hard metamorphic rock formations. The diagram reveals bands of dense dolomite, limestone, and even some metamorphic formations created by the intense pressure of the tectonic boundary. These rock types can be 10 to 15 times harder to drill through than the chalk marl under the channel, Dr. Chen explains. Tunnel boring machines would face extreme wear, requiring frequent replacement of cutting heads at depths where such maintenance becomes extraordinarily difficult. The cost implications are staggering. Dr. Chen pulls up a preliminary budget analysis that shows tunneling costs increasing exponentially with depth and rock hardness. Each additional meter of depth multiplies the complexity of the entire operation. At the deepest points, we estimate tunneling costs could be 8 to 12 times higher per kilometer than comparable sections of the Channel Tunnel. The simulation reveals hot spots where mechanical components would face critical stress levels, areas where failure becomes probable. We're talking about a tunneling operation where the machine itself might be crushed by ambient pressure before it even encounters the rock, Dr. Chen says. To prevent this, we'd need to design entirely new boring technologies specifically for these conditions. But there's another option, a floating tunnel, anchored to the seabed but suspended in the water column to avoid the deepest sections. Dr. Chen brings up conceptual designs for what engineers call a submerged floating tunnel, SFT. The SFT concept would place the tunnel at a constant depth of around 100 meters, regardless of the seabed profile below. It would be anchored to the bottom using tensioned cables, similar to how oil platforms are secured. The animation shows how this innovative design would work. A tube-like structure floating in equilibrium below the surface but above the deepest parts of the strait. This approach circumvents some of the depth challenges, but introduces new ones related to stability, current forces, and potential impacts from shipping, explains Dr. Chen. And we'd still need to anchor it to that same unstable seabed sitting on an active fault line. Dr. Chen walks to a scale model showing various technical approaches under consideration. He points to areas where conventional methods simply break down. The reality is that we're pushing beyond the frontiers of what's been done before. The deepest operational tunnels in the world currently reach less than half the depth we would need to achieve. The engineering is unprecedented.